My name is Peter Kling, and in this brief announcement, I'm going to present you a joint work with Petra Berenbrink and Giakkoupis about leader election in the population protocol model, which appeared this year at Stock. In the population protocol model, we are given a system of n identical agents, each of which should be considered a finite state machine. There are discrete time steps, and in each of these time steps, a random pair of agents will be selected, and these two agents will then interact with each other. So they observe each other's state, and both of them or one of them will update its state according to a given transition function. Our goal in leader election will be to reach a stable leader configuration, which is a configuration as you see here on the right. So there will be exactly one agent in a designated leader state, and all the other agents will be in non-leader states. And stable means here that from this configuration on, there should be no possible chain of interactions that might result in more or less than one leader. A simple example for such a leader election protocol looks like this. So this protocol defines the state space as the orange leader states and the blue minion states. Initially, everybody thinks of himself as a leader, and there's only one update rule here which states whenever two leaders meet, then one of them will become a minion. And it's not hard to imagine that if you now select two random agents, use this update rule, then eventually you will result or end up in a configuration with exactly one leader. Now, if you look at the most recent results in leader election for population protocols, there are two lower bounds which are of interest. So the one by Alistair et al. From 2017, who showed that if I give you agents that use at most log n many states per agent, then the number of expected interactions you require to elect a leader will be an expectation roughly n squared. And very recently, there was another bound by Sudo and Masuzawa who showed that no matter how many states I give you, you will always require at least n log n many interactions to elect a leader, both in expectation and with high probability. Now, on the positive side, the most interesting results here are due to Gazianec et al., who first showed in a breakthrough result that you can use only log n interactions asymptotically to get a runtime of roughly n times log squared. And then later on improved this actually to n log n log n interactions in expectation. So the obvious open question here is, what about this gap? And in our result, we show that you can actually elect a leader in the population protocol model using only log n states per agent asymptotically, and do this in a number of interactions, which is roughly n log n. Okay, in the following, I will give you a very brief overview of our protocol. Our protocol consists of two stages. Stage 1, consisting of these 5 protocols below here, and stage 2, which is actually much longer, consisting of 3 protocols. So let's first take a brief look at stage 1. In the beginning of stage 1, we do something which is very common nowadays in population protocols. We first elect a junta of marked nodes, which has size roughly n to the 1 minus epsilon. This can be used to create a phase clock to synchronize all of the agents throughout the execution of our protocol. And in particular, this allows us to introduce such phases, as indicated here by these red lines, which have length n log n interactions roughly. And we use this to separate the different subprotocols. So basically, this allows us to end one subprotocol, for example, here, and then move on to the next subprotocol in an orderly fashion, which requires some technical details, but this can be done. Now, typically what you do in such population protocols, or what previous work did, is you start with such a junta, which we even reduce a little bit further here to roughly size square root n, most square root n. And then from here on out, you reduce further using different subprotocols, you reduce the size of these marked nodes further. First to polylogarithmic number of agents, then to a constant number of agents, and then finally to a single leader. And you do this in a monotonic way. Now, as you can see here, we do something different. So given this junta, which we selected at some point, we actually first increase the number of agents again to roughly n to the 3 over 4. And note that at this point, we actually have an upper and lower bound. This is different from here. Here we only have the upper bound. And this is quite important, it turns out, because our main idea can be roughly described as follows. Imagine if at this point we would not only have the upper bound, but actually a tight bound of roughly square root n many marked agents. Then it's easy to see that we can go from here to polylogarithmic many nodes in n log n interactions by a quite simple process. The idea is just whenever two of these square root n marked nodes interact with each other, this happens with a probability of 1 over n, then these two guys will create one new node which will be of this population. So a survivor basically of this phase. And you can imagine if this happens now with a probability of 1 over n per interactions, and you look at n log n many interactions, then there's a good chance that at the end of this process you will end up with polylogarithmic number of survivors here. Now the problem why we cannot really do this is that here we only have an upper bound. So if here we have much less than square root n many nodes, then for two of them to meet would take much longer than n log n interactions. So not even a single interaction could happen within one phase. So this would take much more time. And to circumvent this issue, what we do in this phase here, and this is done by our dual epidemic selection protocol, we actually use this population of at most square root n nodes to build up a new population which has size pretty exactly n to the 3 over 4. Here we also have now the lower bound. And using this population, we can use a protocol which is similar to the one I just described, just a little bit more complicated, to get down to these polylogarithmic many leader candidates in n log n interactions. So this is done by this square root elimination protocol indicated here. Now, once we are at this polylogarithmic many nodes, there is kind of a known set of sub-protocols which you just need to tweak in the right way, which will then allow us to go down to a single leader. For time reasons, I won't really go into the details here. Instead, I just want to give you a very brief glimpse of one important protocol in stage 2 and how this is used in the analysis. So in stage 2, there is a protocol which we call slow stable elimination, and here you basically see the corresponding transitions. It's not really important now how they look, but this protocol basically really is responsible for defining who will survive, who can still survive, and who is out of this leader election tournament. Our analysis is based on this protocol, and it considers 3 cases. So the first case basically assumes that everything works out as it should. So basically everything I just described to you for the first stage kind of works out as we hope it would. And we can show that this happens with quite a good probability. So the probability is 1 minus 1 over log n. So this is, for example, to build up this new population of n to the 3 over 4, we get this probability that this works out. And if this works out, we can show that our overall protocol will elect a leader in expected time n log n interactions. So together, this gives us a contribution of n log n to the expected stabilization time of our protocol. Now, the second case here is a little bit worse. Here, we still have the synchronization into these different phases, but we assume that stage 1 might completely fail, and only kind of this last part of our protocol, so in particular the slow stable elimination stuff, works. Now, the probability for this case is then 1 over log n, since this part failed, basically. And then the probability that the synchronization still works is still quite good. This is actually 1 minus n to the minus 3. So this really holds with high probability. Now, here we get a slightly worse expected stabilization time of n log square n. But since this only happens with probability 1 over log n, we again get a total contribution, which is n log n here. And then the last case actually looks at the case that everything falls apart. So even our synchronization does not work, and nodes might be in quite different phases during the execution of the process. And one can show, which is not too hard, that in this bad case, you have a polylogarithmic runtime, which is n to the 3 interactions. And since this happens only with very low probability, the total contribution of this case is quite small. So, and this allows us then to get this expected runtime of n log n. All right, this is all I can tell you in the 10 minutes about this result. If you're interested, I hope you will take a look at the brief announcement or maybe even at the published version at Stock this year. You can also find the Stock talk on YouTube, actually, or I would be very happy if you join us in the online discussion of this brief announcement at PODC. Maybe just very quickly, I want to mention one of several open problems in this area, which is quite interesting. So the result I just presented to you looks at expected runtime. And if you look at the high probability runtime of our protocol, this is still only n log square n. And it would be very interesting to see whether one can improve upon this. So while there are some protocols which require less time, n log n interactions only, these are not state optimal. And it would be really interesting whether there is a protocol which solves leader election in truly less than n log square n time, and still only uses roughly log n many states. All right, that's it from my side. Hope to see you in the online discussion for this brief announcement. So bye.